All right, so we left off with the setup of our problem, and we left off discussing the fact that the overall balance, the air balance, and the hexane balance are not the same thing. And remember that our strategy for solving this problem is to find this number right here, this V2. And our strategy, let's write it down, is we're going to try and find N2, because if we have N2, we can go to M2, and if we have M2, we can go to V2. We know that these two are related via density. So we could go look up density of hexane. And these two are related by molecular weight. So we could look up molecular weight of hexane. So the strategy is to find that N2, convert it to an M2, get a V. If we got a V, we can get a T. All right, let's do that. So let's start, how about with an air balance? The air balance, if you remember, we said that in the air balance, the input equals the output. So what that means is that N air 1 with a dot over the top equals N dot air 2. Now remember, we can rewrite these in terms of the total flow or in terms of the fractions, and in terms of the fraction, not or, and. So let's take Y air in 1 times the total flow in 1, and that's going to be equal to Y air 2 times the total of N2. Hey, check it out. This is the variable we're looking for. So let's solve for it. So N dot 2 is going to be Y air 1, N dot 1, divided by Y air 2. Now the next question for us, let me see if I can refocus again for you. There we go. Is going to be, do we have all those numbers? And the answer to that question is actually yes. So N dot 2 is going to be equal to what comes in, which is actually just 1, times the flow rate in, which is 0.1 kilomoles per minute, divided by the fraction that comes out, which we said was 0.9. So that total flow rate out is going to be 0.11, repeating kilomoles per minute. Okay, so look at that. We've got N2 out. That's super, super helpful. Now, there's a couple questions we can actually ask ourselves right here to see if we actually need to do this procedure that we came up with, right? Here was our original procedure, right? Let's go get a molecular weight, let's go get a density, let's get a mass, let's get a volumetric flow. But what if we don't have access to a periodic table or the density? Normally we get provided with those things. Instead of doing all of this, could we instead take this flow rate and do something similar to what we did here? Let's say, for instance, could we say, we know that the molar flow rate in terms of, let's say, kilomoles per minute will be equal to the change in number of moles in terms of kilomoles per unit time. Could we do that and find time in terms of minutes that way? Is that a possibility? So it actually is, but we have to get the number of moles, right? We don't have this right now. So what we could do is we could think through how could we actually get this number of moles? Because it is actually possible to get this number of moles. It's a little bit different, right? So there's two ways of doing this problem. You could say, wait a minute, I know once I have the flow rate here, that if I have this change in N, then I can find the time and just go from there. Or you could say I have this N, I need to turn it into a V, and we'll go from there. So I'm actually going to do this one right here as a way to show you how to do this. So if you think about it, your N itself is equal to mass times molecular weight. Okay? We also know density equals mass over volume, so therefore mass equals density times volume. What if we put these two together? Well, N will be the density times the volume times the molecular weight. Now we know this volume. This volume is a loss, a negative 10 meters cubed. So we actually can't get around looking up these numbers. We actually have to look up these numbers. So I'm going to give you those numbers because I don't think you need to look them up. And I'm going to tell you that the density of hexane is going to be 659 kilograms per meter cubed. And the molecular weight of hexane is going to be 86.17 kilograms per kilomole. Okay? Now, if we take a look at these units, are we going to get the right units? Well, we got to be careful here, right? This one, this molecular weight, right? We've got to think about what's going on with that molecular weight. And what we see is that I actually wrote this formula incorrectly, right? This should actually be mass divided by molecular weight. So this should be divided by molecular weight, because then our units are correct, right? So there you go. Dr. Lane made a mistake, but I checked it with my units, and that's a great way to move forward. So let's write that full out. N is going to be rho times V divided by the molecular weight. And that's going to be the 659 kilograms per meter cubed times that change in volume. And I'm using negative because we're losing volume from the reactor. Sorry, I went a bit sideways there on you. And then we divide that by 86.17 kilograms per kilomole. And that should give us the right units. And so what we find is that in this system, our change in moles is negative because we've lost volume, and that is actually 76.45 kilomoles. And that's kilomoles of hexane in the system. I'm sorry, I keep writing C6H4. It should be C6H14. That makes a whole lot more sense, doesn't it? Let's fix that. There we go. All right. So why did we do that, right? Let's remind ourselves. Let's draw a little line right here, right? This is a little sidebar. If we have the change in moles and we have the molar flow rate, we can find the time in the system. So let's go do that. Let's go find the time. So, all right. So we know that if we look up at this equation, that time is going to be the change in N divided by the flow rate. But the biggest thing that we have to be careful about when we're doing these types of problems is that everything has the same units. So this change in N right here is a negative change in the kilomoles of C6H14 hexane, right? This flow rate that we found up here is a total flow rate in the system. So one thing that we're going to have to be careful about is this N down here also has to be related to hexane. This also has to be related to C6H14. They both have to be related to that compound. And you can see why putting in the chemical formula starts to make it really hard to see everything, right? So instead of saying that it's multiplied by 0.11 kilomoles per minute, that's the total flow. So we need to think about what is actually related to hexane, and that's the 10% that's coming out of the system. So let's go back to our flow diagram. 10% is what's coming out of the system, right? This is the total flow out, but that's a combination of both air and hexane coming out of the system. When we use formulas like this or like this, everything needs to be the same species. So this right here, we need to be very careful. This is I'm sorry, that's not air. That's the total. So if we want to use that total down here, we need to make sure that it changes into hexane. So that's what this is, right? This is Y of hexane coming out into, and this is N2, and so it's giving us this into. See how it gets very complicated right here? And technically, if we think about it, this flow rate right here, is technically negative as well because we're losing air from the system. It's just not accounted for up here. So our negatives will end up canceling, right? So it's a little bit of wizardry going on right here. So if we solve that and we get a number, it should come out in minutes, and that total time is 6,880 minutes of runtime in order to evaporate that amount. So we're not going to see integral balances as much as we see differential balances, but here are some of the key takeaways before we leave this lecture, okay? Some key takeaways, okay? There are two components of the system, but only one's coming in, and there's changes in volume here. So we know we lose hexane over time. And in integral balances, the key relationship is how the flow rate is related to the total amount and the time, okay? We can do three balances, but the three balances are not the same based on the species. And then when we did the air balance, that's just fine to find a total amount. But if we want to find a time down here, when we do a change or an amount, it has to be related to the same compound in the flow rate. And that's why there's that 0.1 here instead of just using the total flow rate. Okay? So these can be a little bit confusing. So take a pause. And if you have questions about this video, I encourage you to write them when you submit your pre-lectures so that we can go over them in class.